After the Midas Touch bumper music intro, KBYP's fourth video concerning power amplifiers. The first three were analyzing mostly the plate with IMAX information. But that should lead to a output power of some value. And the number that IMAX gives for that tube is about 445 watts, I believe it was. Peak envelope, useful output power, 445 watts. From a 400 watt tube? How's that work? The Mighty TR3, 3 JB6 horizontal output tubes. Each plate's rated at 17.5 watts apiece, 52.5 watts total. I guarantee you, because I've measured it very accurately, this radio goes 300 watts PEP and CW. How can it get 300 watts out of 52 watts worth of tubes? That's the question. I have never found a clear explanation of this anywhere. So I'm going to show you the full color explanation. We start with our representation of a sine wave over one cycle from 0 to t. The horizontal axis is time. T is the time for one cycle, a function of the inverse of the frequency. I look at it in degrees. That's 360 degrees, but in engineering and science, they tend to use radians. The problem is to find peak, as specified by the US FCC. We're required to reckon peak envelope power. In the old days, it was input power, DC equivalent. Since it's a half cycle, it's 0 to t over 2. The goal is to then find the cross-hatched area under the curve, which represents power. W sub P might be the peak power, found by peak voltage times current, but we need to know power for a half cycle to get power for a full cycle. To do that requires mathematical integration from the definite limits of 0 to t over 2 to integrate the sine function, because that's the sine function. Sine theta dt. Theta can be resolved as omega t. Omega is radial velocity, radians per second. The sine integrates to minus cos plus c, and instead of t we use theta, which suggests phase angle. So the integral is over the limits of 0 to theta over 2, which is actually 0 to pi, because a full cycle is 2 pi. Half cycle, 180 degrees, is pi. So theta over 2 is actually pi. Sine theta d theta. Theta max is 2 pi radians, 360 degrees. Half cycle is pi radians. So the integral becomes over the limits 0 to pi, sine theta d theta. That integrates to 1 cos, which that's not proper mathematical form, but it's clear. Making a little correction there, that resolves to 1 times cos minus 1 times cos. Cosine on the left evaluated at 0 is 1, evaluated at pi is minus 1. So 1 minus minus 1 equals 2. So for the 180 degree sine wave hump from 0 to pi, the maximum is 1, the area is 2. Real hard math there. The area is distributed over the interval of 0 to pi. Because recall, an area is height over width. So that is the area, which is 2, over the space, which is pi, or the width, which is pi. That becomes 0.637. Therefore, 1 watt peak is 0.637 watts average. Remember, put the leading 0 in a decimal point. Over 1/2 cycle. Not RMS. Very important. Will bring the wrong answer. all that tells us is a relationship between peak and average power. Let's take an example that I know for a fact, and that's a TR3 and TR4, because I've been through them as a fine-tooth comb and verified all these measurements and calculations. 3 tubes in those transmitters. The plates can dissipate 17.5 watts each. That's 52.5 watts total for 3 tubes. We need to convert that to PEP output because that's what the FCC says to use. But we must explain how 52.5 watts steady state dissipation becomes 300 PEP. That's basically 6 times. So we start with over the 0 to pi interval of 52.5 watts average, and that's continuous. The tubes can key down 52.5 watts dissipation forever because that's within the plate limits. We want to convert that over 0 to pi to some peak power. That's just the opposite of what we did in the previous page. So if average, we just calculated, is 0.637 peak, then peak is average divided by 0.637, and when we divide by less than 1, the numerator becomes larger. So 52.5 watts divided by 0.637 is 82.4 watts peak over 180 degrees. For Class B operation, which the TR3 and TR4 finals operate in, double dissipation for 1/2 cycle. 52.5 watts times 2 is 104 watts. So 104 watts average dissipation in Class B for 1/2 cycle divided by 0.637 is 163 watts. And that's extremely close to about the 155 I measure on the bird. And there's more at play there than just losses. And we can't see that without doing circuit analysis. But the TR3 is 300 PEP out. Whereas the other half of Waldo, I realize that's the supposed positive 1/2 cycle. In reality, it's really the negative going. But where the rest of the energy is, and actually where all the energy is that's going to the load, is not in the tube. Because realize by conservation of energy, and recalling in the old days gross average input coming from the power supply to here, that power going in is feeding both tube losses and going over here towards the load. The tube doesn't make any power, it only uses it. So in Class B, that's roughly 66% efficient. That implies the tube's using 33%, turning it to heat. What's really happening is that when the tube conducts through the inductor, it's also discharging this capacitor, which was charged previously. When that happens, both the inductors here and here are charging. When the tube goes open at the end of 180 degrees, the circuit rings. And that is what provides the other, a bit less than half of the output. And it's not half, it's a bit less. And the trick is that it's reduced not because of losses, but because nothing is supplying additional drive over that 1/2 cycle. So these components are discharging. And as they discharge into the load, the amplitude drops. And in a worst case, it looks like that. The positive peak is the 1/2 cycle we just analyzed above. The negative is supplied by a tuned circuit in a damped system. Recall the damped cases, underdamped, critically damped, and overdamped? Well, this is a heavily overdamped case, and it can attenuate that negative 1/2 cycle pretty quickly because the tube isn't driving anything in Class B during that interval. So the shortened and tilted wave shape is a result of these reactive components giving up their energy to the load, and they can't do that forever. So the ideal would be to have that negative half cycle reasonably close to the positive, but they'll never be the same, because during this interval from 180 down to 270, the system has discharged a considerable amount, so the negative peak down here is raised. For a better example, assume that the switch is a tube. It's operating in Class C. It closes instantaneously. It makes a pulse. This circuit's found in the Radio Engineer's Handbook by Terman. But when that closes, the B plus supply charges the inductor very, very fast with a lot of energy. The tube opens, and the rest of the cycle is supplied by this parallel network ringing out to the load. So that's where a 52 watt amplifier generates 300 watts of PEP out. And I have never, ever seen this analysis. And this is the complete analysis, except for analyzing the sources of this distortion. But that goes into not just the matching network and this inductor, but analyzing the energy storage in those. And this is, it's not obvious, but this is related to the Q factor of the output network, but also the plate inductor, and that is not a choke. And that has been mistakenly called a choke since 1935. But if it were a choke, no RF current could flow through the tube or out through the network. That inductor is calibrated to the energy being drawn. But the goal, as Terman states, is to have this parallel tank, or say a pi network. That's actually an L network. But to have the output network have enough energy to satisfy the last half of the cycle, but not have too much left over. Where the operating line of the tube becomes very important is in selecting the value of that capacitor. We normally call that the plate blocking capacitor. Capacitors need to be rated for DC voltage, which is, let's say it's 2 kV here. So 2 kV capacitors through the inductor to ground at steady state. So 2 kV DC here, plus the two-way swing of that tube, and we don't know what that is without doing the load line. So without doing the load line, we can't pick the value for the voltage for that capacitor because it must be DC plus AC swing. Very important. Too low, it'll break down and blow up. Too high, the capacitor is too large and costs too much. Then after that, network analysis is necessary to find the voltage ratings and current ratings for the rest of these network components. So that ain't rocket science. That's just a little mathematical grunt work. And I'll leave it to you to come up with a handy-dandy formula in which you can plug average plate dissipation in and get PEP out. Okay, BYP.